I think it means from Scotland, which is a little bit similar to New Zealand, at least shipwise.
Okay, so I'm going to talk about a slightly different set of problems and more how a mathematician looks at a problem, and then give you some sense of some results and some things. So this is work with Stan Zachary. Now. So what I'm going to do is I'm going to spend a little time at the start just thinking about what I mean by flexibility and what we mean by flexibility and how we use flexibility, and then think about how we can sort of think about flexibility within sort of an economic framework for various types of flexibility problems and how you might use flexibility, and then give you two examples of some work we've done on actually using flexibility and actually looking at how you actually control flexibility to look at specific types of problems. So looking at adequacy, so this is a problem of I have a demand shortfall, you want to use my flexibility to deal with that demand shortfall. How can I do that? How good can I actually do in that situation? What sort of demand shortfalls can I deal with? And then just talk about some work we did looking at using flexibility to make money through arbitrage in the market and the more market concept. And then finally I will put up two questions, which I'll come to at the end, but where we might be going, where we might be thinking of moving in the future. So what am I thinking of as flexibility? So flexibility comes in a lot of different forms, and it comes in a lot of different scales at different points in your network. So we have the sort of traditional flexibility we have in our networks, which is spare headroom in our generation capacity. So we're running our gas plant, it's not running at full capacity. There is a spare bit of headroom there we can use for flexibility. And recently, through the capacity market, we've been gaining flexibility through diesel generators. Often these are diesel generators which are sat around in companies already for other purposes. So for example, a milk firm might have a diesel generator as a backup generation if they lost supply for some period or whatever and needed this. And now they're looking to monetize those through various markets, both in the distribution level and the transmission level, because they're sat there and they might as well make some money out of them. Then we have our storage facilities, and we have our big storage. So we have the Norwich as our big pumped hydro storage in the UK, but other types of storage are coming online and people are talking about being useful. So batteries, flywheels, compressed gas, making use of storage which is there for other purposes, so uninterruptible power supplies. And everybody talks about EVs, and EVs will in some sense act as storage within these systems. And finally we sort of have what is the child to come, and we don't really know how we're going to deal with it properly yet, but we know it's there. Some of it we know how to do already, which is our dynamic demand reduction. So we already know that we can turn off big industrial users, and we have contracts in place to do that, but we're now looking at more dynamic demand reduction in sort of more domestic settings through aggregators, and also again through our EV charging. And how do we go about using our flexibility? What is flexibility useful for? So flexibility has a whole range of uses. We have sort of had adequacy, both on a national level, so through the capacity market, but also within the distribution network operators who are looking at using adequacy to defer network reinforcement and to deal with issues where they have embedded wind within their network. It can be used in arbitrage and energy trading, so to flatten our markets through a market mechanism, fast response, voltage support, and reactive power support. And as was mentioned in the previous talk, there are a whole load of scales for what we're doing here, both in the spatial and the temporal scales. So in our spatial scales, we have flexibility at different levels of our network. So going through the different stages of our distribution network, it plays different roles, and then going up to our big storage and our big flexibility within our transmission network. But similarly, the different uses of storage have different timescales. So we have the milliseconds of our fast frequency response, moving up to seconds for our fast response and our voltage support, moving up from minutes to our balancing and our actually balancing, hours where we're playing in the electricity market, and then adequacy where we're building and we're making decisions on our planning horizon. And often we will need to understand how we use the storage in an operational time frame to then feed into using it and understanding its role within these longer timescales. So especially when I come to talk about adequacy, I will be talking about it sort of on an operational timescale, but the understanding its operational usage is key to then understanding how we feed that in to our planning timescales and how we actually think about storage and demand side response going forward in our planning. Okay. So I'm going to claim that for a lot of our problems we can think about it in an economic framework, and we can think about how we might use storage within this sort of economic framework from an operational point of view. So we have some flexible resources, and at each time point we carry out an action from each of our flexible resources. And for most of the actions I'm going to think about here, we're going to be thinking about either supplying energy or removing energy from our systems, or supplying power or removing power from our systems. And this is set up in a discrete format. You can set up this in a continuous format as well, and for the adequacy problem in a moment I will set it up as a continuous problem. But the idea is that we're maximizing or minimizing either a cost or a profit over some time, so we're looking at taking this over a time period. Where we have some randomness, we might have randomness in what's actually going on, so we have some expectations attached to this. And we have an associated F, which is then going to be our cost function. This is actually how much we have to pay. And then we have the actions, the total actions by all our flexibility within our network. So what might we be thinking about for this F? So in the case of an arbitrage, this will actually just be the cost of supplying energy into the market or buying energy from the market. Whereas for adequacy, we could think of this now not as a market cost, but a cost for unserved energy. So we have our demand. If I don't supply it, I pay a cost. If I supply it, I don't pay the cost. But again, if you think about it for a moment, it will sort of fit into this sort of framework, and think about it in this. So this is fairly nice, this is fairly simple. But now all the complexity here doesn't really come in what we're optimizing here, but in actually what we can actually do with our systems. So it actually comes into thinking about what are the constraints that the different types of flexibility put on us in our usage. So I'm just going to go through each of those sort of three types of flexibility. So our sort of thermal, then our storage, and then our demand side response, and give you some feel for what are the sort of conditions that you have to put in. So thermal, lots of people have done thermal. It's a well understood thing. So we all have normally a maximum power constraint, but we also then have a ramping constraint. So this is especially true for sort of headroom and questions about headroom. But actually, if we're now going to start putting in cases where we have diesel generators, they might also have some fuel constraint attached to them. So they might have a limitation on how long they can run for. This is not meant to be exhaustive, it's meant to just give you a feel for what's going on. So storage, the three sort of big features of storage people think about wanting to put in are round-trip efficiencies. So now rather than putting in energy and getting the same amount of energy out, I put in an amount xt and I only get an epsilon xt out later on. So this top is a way of capturing that. We have a power constraint for our system, so we can only move in so much energy and out so much energy at each time period. And we have an energy constraint, so our storage has some capacity. There are other things you might like to include, and I don't have a clear way of doing that, and this is still ongoing work and ongoing research. So things you might also like to include for storage are things like battery condition. How I use it affect the condition of my storage and the lifetime of my storage. Similarly, if I put energy in, there's often leakages in storage and a leakage efficiency. So how do I capture that in a coherent fashion? So I just want to, as I say, demand side response is becoming a much more important thing in what we're doing. So I just want to spend a little time thinking about demand side response. So we have our sort of traditional demand-side response to the industrial customers, but through aggregators and various other things, we're looking at now much more demand-side response on the consumer side. Often you'll hear it as virtual storage, and I'll talk to why we can think of it in many applications as virtual storage in a moment, but really the big reason is it has very similar constraints. But it can be quite different as well. So I'm just going to break this down into two. So we have our industrial demand-side response, which has our power constraint as before, and it will often have an energy constraint as well. But an extra thing we might care about, it might have a time of use constraint. So I'm only allowed to use this at certain times of day. For a domestic aggregator, we think about these. You will notice again are my three constraints I had for my storage. So we can think about it having a very similar set of constraints as we had for our storage. But we might again have other things we need to care about. So for example, often there's an elasticity issue in demand-side response. So if I switch off your fridge now, you really would like it to cool down sometime in the next hour or two, so I have to repay that debt sooner rather than later. Whereas if I put in some power into the Norwic, it can sit there for days, weeks, years, and I have no constraint on when I have to take it out again. So we need to carefully think about how we might include a repayment cost into our models for demand-side response. But having said that there are these problems and there are sort of things, it's important to take a step back when you're setting up your problems and to really understand the problem you're solving. Because though we have these big lists of constraints, some of these constraints become, if you think about it carefully, become unimportant for certain settings. So we have a situation where not all those constraints are important, and that will often lead to a simplification of a problem. So for example, we will often be in a situation where the repayment debt isn't going to be important to us because actually the action time we're looking at is small enough that actually we haven't hit that repayment threshold. So we will repay anyway in our system even though it doesn't come out. So for example, if we think about this adequacy problem, in the UK our adequacy problem is really about peak demand in winter. That is a short period of time that we're talking. We're talking a few hours at winter peak. So they are short and they are continuous periods of demand. So there are a couple of interesting things which this means in terms of thinking about constraints in our systems. So given a contiguous period, we will continuously be using our resources within those periods without any chance for recharging of our storage. The sort of mentality that we're in is we will use the resource and then recharge at night, which is well away from any our adequacy periods, so we don't really care about the round-trip efficiency. And we don't care about feeding power into our system, so we don't care about the input power constraint. And we will always consider our storage to be full at the time. And again, we now have this short time scale, so when we're thinking about the demand-side response, our repayment horizon isn't there because by the time we have to repay, we're well out of the event that we care about. Okay. So, just a little example of some case study now for adequacy. So we have a problem, and I'm just going to look at the solution to the problem and how we can set up this and give you some examples of a solution. So we have a demand process. This could be a stochastic demand process, or it could be a deterministic demand process, and we have a set of stores. And I'm going to, for a moment, think about all my demand response as virtual storage. So this is really just thinking about storage and demand side response. I'm ignoring the sort of traditional flexibility because they will just add capacity, and we'll just use them. So each store can serve energy at a rate Ri, and it has some power constraint. So now this is my constraint, how quickly I can empty my store. and it has a capacity constraint. So this is the total amount of energy within the store. And we want to look at the adequacy problem. So what we want to do is we're now going to have our demand process, and we then have the amount of power we feed out of our stores, and we will pay if I fail to meet that demand. So if I fail to get enough power at my stores to meet that demand, I'm going to pay, and my total payment over the entire event I care about is just going to be the total energy I didn't serve. And I have an expectation here because I allow my demand to be random, and then I have my two constraints, my power constraint and my energy constraint. So in one of those slight quirks of academia and people working on interesting problems at the same time, I'm going to give a solution to this problem. Turns out another group at the same time came up with a nearly identical solution to a problem in one of those cases. So if you want a slightly different perspective on the problem, then you should also look at the work of Evans, Angeli, and Tindemans. They have a very nice set of 3 papers which address nearly identical problems and come up with a nearly identical solution. There's a slight tweak at one point where they integrate one way and we integrate the other, but pretty much the same solution. And it was one of these cases where we were writing the papers and doing the work at identical time, and just by a chance meeting we discovered we had exactly the same results at the same time. Okay, so how do you go about solving this problem? It turns out that there's a nice optimal solution to this, and it's a nice optimal algorithm which is very myopic to what goes on. What you do is you take your stores, you take them and you calculate this E over P ratio. So this is the time to empty if I run them at maximum power. We order our stores by this ratio, and then we act in a greedy fashion. So we always try and meet the demand as much as possible at every point in time, and we do it in a priority order by this E over P ratio, and as soon as we equalize this E over P ratio, we then act proportionally. So, for example, at the bottom here, 2 stores, and we have a demand. This store on the left has a bigger E over P ratio, so we prioritize that store. We take out that demand from that store. We've now equalized the 2 stores. We now have another demand comes in, and we act proportionally on the 2 stores. And this is provably the optimal thing you can do in this case, whether you're in a stochastic environment or a deterministic environment. So you can then start thinking about related questions. So now, if I have a set of stores and I now give you a demand function, can I meet that demand with the set of stores? And it turns out there's a very simple way of doing this and a very simple way of answering this question. So the first thing we do is we take our demand process, our deterministic demand process, and we're going to just reorder it so it's a decreasing function. Reordering is not a problem. If I can satisfy the reordered thing, I can satisfy the original thing. So I've now got a demand profile which is a decreasing function in time or power, and I can create a store process, a store profile which takes all my stores and stack them by my E over P ratio to give me a power time curve for my stores. So now, okay, this nice graphical representation of our demand and our stores, but now how do we actually use this? What we do is we say, okay, at every time we find the total amount of energy I actually supply in my demand process and the total energy I could have supplied for my store process, and as long as the total for my store is always greater than the total for demand, then it's going to be the case that I can satisfy that demand profile. So it's very easy to check the converse. So it's very easy to check that if this area was bigger than this area, I wouldn't be able to do it, because this is the maximum energy I can supply by that point. Whereas, so if I don't have that amount of energy, then I couldn't have satisfied that problem. It takes a little bit more to do the converse to check that you really can do it, but you can prove that this is all the condition you need to check in that situation. Okay, so another little toy thing you might care about when you're thinking about demand and stores is how, if I give you a store and some stores, how much do I actually have to provide in firm capacity to give me an equivalent reduction in expected energy unserved. So it turns out that it's sort of obvious it depends on the demand profile, but it also depends in quite an interesting way on the number of stores. So just a graphical view of what we're trying to think about here is we have a demand and some stores, and now I'm going to ask I have a store and I have some firm capacity, what is the equivalent amount of firm capacity which will give me the same reduction in the expected energy unserved in this case. So just to say why it's a little bit more interesting than it might obviously be, immediately if we think about a toy example now where I have a single store. And turns out there are two sort of cases here, one where you empty your store completely and one where you don't empty your store completely. So my left case is where I'm not emptying my store completely, so it's green is what the store would have satisfied anyway, but now the firm capacity, if I add just a small amount of firm capacity here, it's changed the energy unserved is only going to be the length of time at which this store couldn't satisfy times by the firm capacity. Whereas in comparison, if I have a situation where I empty the store completely, I can add a firm capacity now which is the entirety. Its reduction of EEU is going to energy unserved is going to be the complete length of the event times by the amount of capacity. So we have to be very careful when we're thinking about firm capacity in here, and we have quite a nice little result in that, but it's quite technical in nature. Okay, so you might, if we went back to the start, you might complain to me that energy unserved is not a good measure necessarily to actually look at. You might instead care about weighted energy unserved, because the first megawatt I shed is certainly not as valuable to me in some sense as the 100th megawatt I might shed from my load. So we might care about some weighted system. So we now have a convex, and it turns out that as long as my weighting function is convex, the solution is the same, because there's this nice property of convex functions. So how do we do this? So it turns out now that you can't be greedy. So I'm only going to talk about in the solution of a deterministic case. But it turns out you can do something very nice, which is you can say, okay, what is the optimal solution if I just have one store? So the optimal solution if I have one store is to find a level K, such that above that level K, I will serve energy as much as I can. So I serve to my power constraint and then up to level K in the case, and I pick K so that at the end of that time period where I'm serving, my store is empty. And then I have some new residual demand after that. So that's how you do one store. Turns out if you have more than one store, all you do is you do them sequentially. It doesn't matter what order you do them in. You just schedule them sequentially. So you have one store, you take your residual demand from the previous case, and you do exactly the same thing. You schedule that one store optimally. Your second store optimally now with the residual demand. Doesn't matter what that first store, as long as it comes with residual demand. Again, you select this level K, and you serve optimally for that K. You can prove this is now optimal, and it doesn't matter what order you do the stores in. We'll still give this optimal policy. Okay, so that's adequacy. I'm not going to go into the details of flexibility in so much detail, and I'm going to show some rather unpleasant mathematics at some point. But I just want to give you a sense of what we can do here, and the fact in a sort of very similar framework we can get some sense of what you should be doing here. So we're going to be playing in the market, so we now have a cost function from the market to the amount of energy we have buying or selling on the market. But we also might have our storage being used for other things, so there might be other costs to us operating our store for other services we've agreed to provide. So how do we operate a store in that situation? We can set up a problem which looks very much like the economic problem we had before. Now, let's break this down. This is our cost function for buying and selling electricity into the market. And then our AT is going to be an expected cost for having our store at a specific level. We have our energy constraint and we have our power constraint. So what am I hiding in that AT? I'm hiding a couple of things in that AT. So I'm hiding firstly a cost if I have a call on my store from some other random event which I've agreed to provide for, and I haven't got enough energy in my store, then I might have to pay penalties there. So that's my first part of the AT, is hiding that cost for not being able to provide a service I've already contracted for. Similarly, if I have a random fluctuation, I will have lost some energy in my store. So AT also hides the value of that lost energy to me. And I might also have some reward for having energy in my store. So maybe I'm being paid for reactive support, where actually I'm not losing any power out of my store in the long run, but the fact I have energy in my store pays me money. So I set out that as a deterministic problem. Turns out that it really is, there is a really stochastic dynamic programming problem, which that is just a careful reformulation of, where the optimal strategy, the strategy you take for solving that full stochastic programming problem, is you solve the deterministic one, and every time you see a random event, you just go back and you resolve it. And it turns out solving that deterministic problem is quite simple, so it's not really a problem in terms of cost, and this is quite a well-studied way of solving these sort of problems in the optimization literature. So we can do it. I'm not going to go into the details of the theorem of how we do it. We can do it. And you do it using some Lagrangian things. Gives a very nice policy in terms of how you actually look at minimizing it. And then just a final slide of we can actually do this, and we actually can do this with some real data. So this is taking some prices from de Norwich with a specific type of function AT. Okay, so I want to just finish by putting two questions to the audience, which is, firstly, I've talked about adequacy and I've talked about arbitrage. I put up a list of other cases where you might care about flexibility. So what are those areas that we as mathematicians should be looking at in detail? What are the other uses of flexibility where we don't really understand how to use it well yet that we should be looking at? And I put up a various list of constraints for different types of flexibility at the start. So the other question is, what are the other features of our flexibility that we're missing and we need to properly capture in our models?
Thank you very much.
Hi, Catherine McClay, National Grid. That's a really great presentation. Thank you very much. Can I perhaps add another question rather than add to those? So I've got a team under me that advises the government on derating factors for storage, etc. And one of the key features of our market, all our markets, is their self-dispatch. So one of my questions is, as we get more and more diverse storages, etc., can a self-dispatch market deliver an optimal solution? Because when we looked at the capacity market, what you do to maximize your profits as an individual might look quite different from what you should do optimally for the system. You don't have to answer that.
I think that's an interesting question, but
I think it's one that we've been mulling
Can I
over.
make a comment on that?
Yeah.
Because I'm somewhat involved
Yeah.
advising you on that. When you actually work out the value to capacity markets, you assume that you are able to optimize the dispatch.
Yeah, and we can't.
And you can't.
Yeah.
And that's a really big problem.
Yeah.
And in the case of storage, there is an absolute need to coordinate it in some sense, kind of everybody providing at the same time. And so I think that's a technical problem that you have to solve between the system operator and the stores.
Or it might actually be a market design problem as well for the capacity market. I think Paul's got something.
I was going to maybe.
I was just going to be a little bit more concrete on that. Yes, I think it is a market design problem.
Sorry, could you please introduce yourself?
Sorry, Paul Troughton from Analytics. We're a demand response aggregator. But what I thought was interesting is your comments on equivalent firm capacity. The way that's calculated in the capacity market for storage limited with limited duration, the assumption is that everything is dispatched at the same time, regardless of its duration. at the beginning of a stress event, which is clearly not optimal. And it seems wrong to be designing your market around the assumption that everyone will be doing something quite silly.
Thank you. Well, do you want to reply?
No, I think.
Okay. Yeah, Patrick, please.
Yes, very interesting. So I have some concern about this aging process. I'm afraid that you will use always the same batteries. So could you elaborate a bit on that? Could you put something on the...
So I think that's an interesting problem, and definitely it adds a coupling through multiple events, which at the moment we're sort of looking at single events and they're not coupled, but actually if you care about the aging, it will couple multiple events together. And I think you can do it, I just think you have to be careful about how you would do it. And it's definitely an interesting challenge, I think. And understanding things about aging, but also with aging you also lose certain capacity, you lose energy capacity in your battery, so how do you capture that properly in your things? And your understanding of your charging your battery is not entirely clear always, because the way we sort of model batteries is a little difficult as well.
Okay, another question. Simios, please.
Thank you. So to answer the question actually, but also to set a question based on my answer, I think there is also locational value in storage and flexibility, which is something you could, let's say, in principle, look when trading over a network. But I wonder if the mathematical framework breaks down, especially the prioritization over the E over P ratio when you take locational value.
I think the locational one is an interesting question, but actually for the adequacy one, it turns out, I think, having spoken to some of the distribution operators in the UK, they often have one pinch point they care about, and so that they can think of the points behind that pinch point as a single unit. So, and they don't care what happens elsewhere for that pinch point, because it really is either a line or a transformer pinch point that they are looking for adequacy issues on, and therefore you still can do this within that geographic region.
Okay, thank you. I think we are eating into our break, and so let's thank once again the speaker. We have a tea and coffee break.